Okay, so good morning. And the idea of the lesson today is to go on with the description of the effect of the motion of the ions on the properties of the solid state. And let's say, as I anticipated to you during the last lesson, the idea of allowing the ions to move with respect to their equilibrium position, comes from many experimental details that give indication concerning that let's say the model where the ions are fixed in their positions may not be the best way to describe the properties of the lattice. Now the idea is to, let's say, to allow the ions, the general idea is to allow the ions to move with respect to their equilibrium positions, but to keep the vectors of the Bravais lattice as a reference also in case the ions undergo a motion. So if this is, let's say, a short part of the lattice, we, for the moment, we have used, let's say, an origin. So we have chosen an origin in space, and we have used vectors belonging to the Bravais lattice to describe the position of all the ions belonging to the lattice itself. Now the idea is that this ion and all the other ions in the solid has the opportunity to move with respect to this position, but the motion, so this is the old position, this is the new position, and at this point this ion may oscillate with respect to this position. So the idea is to, let's say, describe this deviation from the initial position of the ion with a vector, and the vector is called U in the textbook. And the index of this vector is again the index, is an index that corresponds to the Bravais lattice that correspond to this specific ion. So the underlying idea is that we allow the ions to move with respect to their equilibrium position, but due to this motion, let's say this ion will never be found far away from the initial position. So this will not be observed because in this way, let's say, the deviation from an equilibrium of the ion that is found in position R would be close to the, let's say, position of this other ion, for instance, whose initial position is not described by R. So the general idea is that we have just a small deviation, and this deviation has a parameter, as an index, and the same and the index is exactly the vector that highlights this ion with respect to all the other ions. So we suppose that U of R, that is the deviation from equilibrium, from the equilibrium position, is small. And in a while, I will tell you what is, let's say, what do we mean by saying small. So in this way, we may still use the Bravais lattice or the vectors So we may still use the vectors belonging to the Bravais lattice to access all of the ions belonging to the solid. And in this way, we may, let's say, keep the model that we have used up to now to access all the ions, but at the same time, using this approach, it is possible to allow all the ions to move with respect to their equilibrium position. So at this point, with this idea in mind, it's possible to write down an Hamiltonian for the ionic system, because let's say the process we will start now can be discussed in this way. At first, we will try to describe the motion of all the ions, coupled ions, using a classical Hamiltonian. So we'll start with the classical. with the classical Hamiltonian, including n ions that undergo oscillations with respect to the equilibrium positions. Then after the calculation, we will see, let's say, which kind of motion those ions may describe in the system. And then we will try to see if, using the details of the motion that we will be able to access by solving the classical Hamiltonian, it is possible to, let's say something more concerning the properties of the solid. In particular, the main point that we are still unable to discuss properly, it is the specific heat. So the idea will be to evaluate the specific heat of the solid, also including the contribution of due to the motion of the ions, and to, let's say, after this evaluation, to compare that with the experimental value. And then at that point, we will see whether this approach can be or cannot be the proper one to describe the motion of the solid. So this is the first part of this discussion, because after that, there will be another part that depends on the result of the comparison between the specific heat as evaluated using this approach and the specific heat as found experimentally. So the classic Hamiltonian is the Hamiltonian where we have the kinetic contribution. Now, concerning M, in this approach, I suppose that we have a lattice where all the ions are equal with each other, because that is the simplest case when you want to make all the calculations. There's also the opportunity to have to describe the properties of a solid with with different kind of ions, so that in each cell of the solid you have more than one ion. But in this case, I will just consider the let's say the more simple case, the simplest case where we have just one kind of ions in the system. Then at the end of the calculation, I will tell you what happens in case you have more than one ion per cell in the system. So M is the same in this approach for all the ions. M is the mass of all the ions, sorry, of each of the ions belonging to the system. Then P square is the square of momentum. Here, to say that P square is the square of the momentum of each of a specific ion belonging to the system, I use R as a variable. So P square of R means the square of the momentum belonging to the ion that is in the position described by the vector R. So in this case, this is a consequence of the initial hypothesis that the deviation from equilibrium is small. So I may still use R as an index to access the ions in the system. So in this case, the summation of the contributions of all the ions is over the vector R belonging to the Bravais lattice. Then the motion of the ions is coupled in the sense that each of those ions here interact with all the other ions in the system. So we have to include an additional contribution that depends on, let's say, the interaction potential between the ions. In this case, I just use phi to say phi is the expression of the potential interaction between the ions in the system. And this depends on the, let's say, distance between the ions. So this is the, let's say, static approximation, where static means that all the ions are fixed and they, let's say, they do not interact, they interact with each other but are still fixed. In this case, P square would be equal to 0, because if the ions are fixed, no deviation from equilibrium, then P is equal to 0. At this point, I introduce the deviation from equilibrium. So the position of the ion that was initially described by the vector r is r plus u of r. So in this way, I introduce a small deviation from equilibrium. So in this case, let's say the dynamic Hamiltonian is again the sum over r of p square of r, and in this case p square is different from 0 because we have deviation from equilibrium, so we have the actual oscillation of the ion, plus 1/2 the summation over r and r prime of phi. Then we have r plus u of r, so the new position of ion that was initially in position r minus the new position of the ion that was initially in position r prime. Okay, if we just concentrate on what is found here within the parentheses, this is r minus r prime plus u of r minus u of r prime. So r minus r prime is the, let's say, initial value of the distance between ion in position r and ion in position r prime. Differently, r minus r prime plus u of r minus u of r prime is the, let's say, difference between their positions in the approximation where each of those ions is able to oscillate with respect to the equilibrium position. So when we say that the deviation from equilibrium is expected to be small, what one is assuming is that u of r minus u of r prime is smaller and smaller with respect to r minus r prime. So in this case, the assumption is u of r minus of u of r prime is smaller and smaller with respect to r minus r prime. So at this point, we may consider in this new expression for the Hamiltonian, this deviation from equilibrium as a perturbation of the static problem. So at this point, if this is the potential energy, the contribution to the potential energy in the static situation, and this is the contribution to the potential energy in the dynamic situation, then we may consider the deviation from equilibrium of the ions as a perturbation to the static problem. And this is done to, let's say, to have the opportunity to not consider the full expression of phi depending of r prime and the corresponding deviations from equilibrium. But at this point, the idea is that with this approximation in mind, we may expand this expression for the potential with respect to the equilibrium position. Before going on with this expansion, just a comment concerning phi. So phi is the interaction potential between the ions, but this interaction potential is not the, let's say, pure Coulombian potential referring to positive charges. So this is not the, let's say, pure Coulomb contribution considering ion in position r and ion in position r prime, because the motion of the ions is strongly coupled to the motion of the electrons. So you may suppose that each time you have that one ion deviates from the equilibrium position, then the cloud of electrons that is close to that ion will also rearrange, considering the fact that the position of that ion is no more equal to the equilibrium one, but displays a deviation from the equilibrium. So you have to imagine this motion as if during the motion of the ions, all the electrons rearrange their position depending on the actual position of the ions. So phi depends both on the charge of the ions and on the charge of the electrons. At this point, we may have to consider how fast the electrons rearrange or change their positions depending on the oscillation of the ions. Because if the oscillation of the ions takes place with a given speed, with the given frequency, and the motion of the electrons takes place with the frequency or with the speed that is quite close to that of the ions, we have that phi may depend both on the coordinates on the ions and also on time, because we may have to consider a potential that from time to time changes depending on the actual position of the ions. But as we will see later after this calculation, the motion of the electrons is way faster with respect to the motion of the ions. So we may consider that for each configuration of the ionic lattice, the electrons are always in equilibrium with that configuration. So the electrons move so fast that for any distribution of the ions, the electrons are in equilibrium with that distribution. So in this way, we have, again, a sort of glue that is given by all the electrons that rearrange as the lattice oscillates, but this rearrangement is very, very fast. So we do not have to consider an additional time dependence due to the contribution of the electrons. So let's say even in this approximation that is called adiabatic approximation, so adiabatic approximation means the electrons are always in equilibrium with the ionic lattice. The expression of phi is quite complicated because, again, we have to consider both the position of the electrons and both the position of the ions and the position of the electrons. But so for the moment, I just leave phi without a specific expression. Later, during the calculation, we will see that there is the opportunity to estimate the actual phi dependence on the position of the ions, so to estimate the strength of this potential. For the moment, we just suppose that this potential is a couple potential, so that couples two ions belonging to the system, and the additional approximation is a small deviation from equilibrium. So at this point, we may perform an expansion of the dynamic term, just supposing that the deviation is small. So, oops. Now I just concentrate on the potential term. So the potential term is 1/2 summation over R and R prime of phi of R minus R prime plus U of R minus U of R prime. So we suppose that that is the deviation with respect to the static value R minus R prime, can be considered to be small. At this point, one tries to perform a Taylor expansion of the interaction potential with respect to the initial value, that is R minus R prime. So in this case, we have 1/2 sum over R and R prime, and we have also, I add now something that I should have had before. In this case, we suppose R different from R prime, otherwise you consider one ion interacting with itself. So in this case, the static term is just R minus R prime. Later on, I will find a more compact expression for this contribution. Then the second term in the Taylor expansion includes the gradient of the potential with respect to the perturbation, and the gradient is evaluated in the equilibrium configuration. Now, due to the fact that the ionic lattice, due to the fact that the Bravais lattice is the equilibrium configuration of the lattice, at this point, one expects that at the equilibrium, the gradient is equal to 0, because at that point, when the ions are in their equilibrium position, they are actually in the equilibrium configuration. So in this case, the first term of the approximation is supposed to be equal to 0. So you have no force, no actual force, if the ion is exactly in the equilibrium configuration. Then we have the second order term, where we have 1/2 that should be 1 divided by 2 factorial, that is the coefficient of the Taylor expansion. Then we have 1/2 that is just the 1/2 that we had at the beginning of the calculation. And then we have the sum over r and r prime and alpha and beta. And now you understand what is alpha and what is beta. Alpha and beta are the 3 coordinates. So coordinate 1, 2, or 3, or x, y, z, depending on how you want to represent the coordinate. Then we have the second derivative of the interaction potential . And then we have, I'm sorry, I've write that here below. Yeah, so we have this additional parenthesis. And in the, maybe just concerning the derivative, maybe writing du of alpha may be misleading. This is just to say that the deviation is respect to the coordinate alpha and the coordinate beta. So if alpha is x and beta is y, it is just the derivative with respect, the double derivative with respect to x coordinate and y coordinate. And in principle, let's say you are able, one in principle is able to expand using the Taylor expansion even up to higher orders, so to the third order, fourth order, and so on. But in this case, the general choice is to adopt the so-called harmonic approximation. And harmonic approximation means that the Taylor expansion is performed up to the second order. So one tries to neglect the orders of approximation that are higher than the second one. Is this a problem or not? It's not possible to give here a general answer, because the fact that this approximation is fine or not depends on what you want to describe. Because if you want to describe the melting process of the solid, then the harmonic approximation is not fine, because during the melting, you expect that you have strong deviations from equilibrium. So you may not just stop at the second order of approximation. Even if we do not consider something as strong as the melting process, even if you want to describe the system at high temperature, a temperature below the melting, but higher than, let's say the room temperature, then maybe the harmonic approximation is not fine. But as the, let's say, details where we want to concentrate regard the, let's say, the behavior of the ionic motion at temperatures that go at a temperature that ranges from 0 up to more or less room temperature, we will see that for temperatures in this range, the harmonic approximation may be considered to be fine. So, for instance, we want to investigate the dependence of the specific heat or the dependence of resistivity on temperature. And the experiments we have in mind are experiments that where the temperature, the specific heat or the resistivity are measured again from, let's say, a temperature of close to 0 Kelvin up to 300 or 400 Kelvin. And in this case, the harmonic approximation, that means when you investigate properties at room temperature or at the temperature that is close to room temperature or below, can be considered to be fine. In case one is interested in higher temperature properties, then third orders, the contribution of the third order, fourth order have to be included to have a more detailed description of the properties of the solid. But in this case, stopping at the second order is enough. Now, let's just see if it is possible to rewrite this expression here. Sorry, before doing that, I will also give you another expression for the zero order. So concerning zero order, we have 1/2 summation over r and r prime, and r is different from r prime. We have phi of r minus r prime. Now, r minus r prime is a vector belonging to the Bravais lattice, so we may call this r second. So we have 1/2 summation over r second and r prime, and we have phi of just r second in this case. The only term that, let's say, changes the element you are going to sum up is r second. So the summation over r prime gives just n times n, because if we suppose to have n ions, the number of vectors that are included in the summation is equal to n. So this is equal to n divided by 2 summation over r second. And in this case, I forgot to write here, r second is different from 0 of phi of r second. So this is just another way to rewrite the equilibrium term, so the potential energy that corresponds to the static configuration. I anticipate here something that I will recall that later. Please note that this value does not depend on the actual configuration of the ionic lattice. So here you have no contribution due to the oscillation. So this means that whatever the shape or whatever the structure of the oscillations of the ions, this term will never change. So this is the equilibrium term that needs to be considered if you want to estimate the total energy of the system, but may be neglected if you want to consider, for instance, the specific heat, because this term will never change depending on the actual configuration of the ions, because that depends only on the equilibrium positions, but does not depend on the actual positions of the ions. That means the equilibrium position plus the deviation from equilibrium. So from the point of view of the evaluation of the specific heat, we may neglect this contribution, because again, that term does not depend on the actual position of the ions, and for the same motivation, on their oscillation. So now let's consider the second order term. In this case, we have u of alpha position r minus u of alpha position r prime. Then we have the second derivative of r minus r prime. Just to write that in a more compact way, if you don't mind, I just write alpha beta here as an index to say that this is the second derivative with respect to coordinate alpha and coordinate beta. And then we have u of beta r minus u of beta r prime. At this point, we may expand the two parentheses. So we have u alpha r, then we have the second derivative r minus r prime alpha beta, then we have u beta of r, then we have, so in this term here, the coordinate of the first deviation is equal to the coordinate of the second deviation. There is another term like this one here, that is the one corresponding to u r prime here, and u alpha r prime and u beta r prime. So we have plus u beta r prime second derivative sorry, there is no, this is not beta, this is alpha. So these two terms have the same structure. That means same coordinate of this for what concerns the displacement from the equilibrium position. Then we have two terms where we have to consider r as the coordinate of the first term, and then we have r prime as a coordinate, as the coordinate for the second. So we have one term here, and then the second term, u alpha r prime, second derivative, and then we have u beta of r. Please note that here we have r and r prime for what concerns the deviations from equilibrium. Then we have r prime and r. Now, due to the fact that r and r prime are vectors belonging to the Bravais lattice, we may end r and r prime, again here, are vectors belonging to the Bravais lattice, due to the fact that in this term and in this term, we have just the deviations from equilibrium for two ions, and the order of the ions, let's say, is exchanged, since here we have r and r prime, and here we have r prime and r. What happens if we exchange the two variables? If we exchange the two variables, we should have r here, r prime on the other side, and into the parentheses we have r prime minus r if we exchange the coordinates of the two ions. Now, what happens to the potential if we exchange the order of the coordinates? That means that, let's say, if instead of using this difference, we concentrate just on the vector that is the difference, in place of considering here vector, let's say, r second, we have to consider the vector that is minus r second. But the Bravais lattice has inversion symmetry. So if vector r belonging to the lattice, also vector minus r belonging to the lattice itself. So the final conclusion is that this term here and this term here are equal with each other, apart from let's say, apart from the exchange of the coordinates. So these two terms here and these two terms here are equal with each other, because the only difference between the two elements in the couple is just the labels that you use to access the ions. But the labels are just an index of summation. So even if you change the index of summation, then the final summation is always the same. So the idea is that that this part here, that this term is equal to this one here, apart from the change of the indexes, and this term here is equal to this other term here. So I now just rewrite that expression using a two-factor in front of each term. So what we have is that we have 2 times u alpha of r second derivative r minus r prime with respect to alpha and beta, u beta of r, and then we have minus 2 times u alpha r second derivative r minus r prime with respect to alpha and beta, and then we have u beta r prime. At this point, the question is it possible to make another step in the calculation just to write those two terms exactly in the same way? If you notice here, we have coordinate r at the first place and coordinate r prime in the second place. Let's try to rewrite this term so that we have coordinate r in the first place and coordinate r prime in the second place. So we have twice u alpha of r second derivative alpha beta phi of r minus r prime u beta of r. That can be written as 2 times u alpha r second derivative with respect to alpha and beta of phi r minus r prime. If we write here u beta of r prime, then that is, let's say, this term in this form is different from the first one. So we have included this r prime here to have the same index of summation here, but actually this r prime should be equal to r. So to preserve that, we have to include the Kronecker delta, where we say that r prime has to be equal to r. In this way, we write here r prime, but what we actually mean is r. Now, if we introduce this Kronecker delta, the r prime in this summation disappears because r prime, due to the Kronecker delta, has to be equal to r. So this becomes 0 in this approximation. So to avoid this fact, so to avoid the fact that this r prime is exactly equal to r and this difference goes to 0, we have to replace the r prime in this parenthesis with the new index r second, and to make a summation over r second. This summation over r second tries to replace, I just write here the initial expression. The initial expression was summation over r and r prime of u alpha r So this was this term, the initial term with the summation. So in this case, if we rewrite the things using this new approximation, we have the summation over r and r prime u alpha of r second derivative with respect to alpha and beta of. So this was the initial part. If we set here r prime, then we have to include the delta to bring back this r prime down to r. But if we do that, we lose the summation over r prime because we have this delta. So the summation over r prime disappears. To make that summation come back in its position, because we need a double summation, then we introduce a new index, r second, and we make the summation over r second. So in principle, we have also a summation over r prime that was in the initial expression, but the summation over r prime is, let's say, eliminated due to this Kronecker delta. And then due to this fact, we replace that summation over R prime with a new summation over R second. So in this way, with this new, let's say, redefinition of this summation term, the idea is that this can be written as 2 times U alpha of R d alpha beta of R minus R prime times U beta R prime. Who is D? D is just this matrix, the second derivative matrix, and this new term, so D alpha beta of R minus R prime is the second derivative with the minus sign in front. And then we have plus the summation over R second of D square alpha beta phi of R minus R second Kronecker delta R prime R. So this is the full expression of D. The important thing is that thanks to the introduction of this matrix, then we may just rewrite in a more compact way the potential term. So due to this redefinition of the potential term, we have that the actual Hamiltonian is equal to the summation over R of P squared of R divided by twice the ionic mass plus we had 1/2 due to the initial term, 1/2 due to the Taylor expansion, these two factors that comes from the, let's say, expansion, rewriting of the of just the potential contribution, and then we have the summation over R and R prime with R different from R prime. Just to avoid the summation over alpha and beta that I should write here, I just write U as a vector. So U of R is the vector corresponding to the displacement of the ion in position R. Then we have the matrix corresponding to the distance R minus R prime, and then we have the displacement corresponding to the ion that is in position R prime. So in this case, this can be simplified with this. So we have just the D 1/2 in front of that. And yeah, this is just, again, a way to, sorry, I forgot the equilibrium term. Yeah. So in principle, there are higher orders of approximation, but we stop here at the second order. Okay, so for the moment, two approximations. The adiabatic one for what concerns the motion of the electrons with respect to the oscillation of the ions. The second approximation is the one concerning the harmonic one. So we stop this Taylor expansion at the second order, and this will be fine for the investigation of the properties of the solid in a range of temperatures that goes from, let's say, close to 0 Kelvin up to room temperature, or even some hundreds of degrees just above room temperature. Okay, at this point, we have no new information. We have just written in a different way the Hamiltonian. To solve, so at this point, the problem is to to find u of r and u of r prime, or in general, the displacement u of r. How is it possible to make an estimation of u of r? We have to make an hypothesis. So at this point, we have no constraints concerning u of r, but one tries to do is to make this approximation. So one tries to suppose that u of r is just let's say can be described by a plane wave. So I introduce now something that I will recall later. As I have introduced that to you, u of r is the displacement of the ion in position r. So it's a variable that is strongly linked to the specific position of each of the ions. But please, in your mind, start to, let's say, consider u of r not as the displacement of all the ions, not as the displacement of a specific ion, but as a displacement field. So something that is defined in every point, in all the points of the space, that is evaluated at the position corresponding to ion that is labeled by R. So please consider u of R as a general field, a scalar field, not actually a scalar field, a vectorial field that tells you what is the displacement as a function of position, but then as the ions are not continuously distributed, but the ions occupy just a specific position, then what you do is to evaluate this displacement field in a position that is equal to R, so that you have the actual displacement of the ion that is in position in the position labeled by the vector R. So please consider this as a continuous vector field that you evaluate only in discrete positions. So this continuous field may have, let's say, an amplitude. For the moment, the amplitude is not important. I just put there a coefficient to say that in principle you have also an amplitude. Then you have the plane wave structure. So you have a wave vector and a frequency. So you have both a position dependence and a time dependence. Then, since we have to describe the motion of one ion in 3 dimensions, in free space, then the motion may take place along a specific direction. So here we put E, that is a vector and represents the direction of oscillation. Due to the fact that here we have an amplitude, we may suppose, and that will be clearer later, that this vector has a modulus that is equal to 1, so that is a versor, but we will see that, we will check that later. So for the moment, let's just write down this as this continuous field, this evaluation of the continuous field in position R as an amplitude times a phase, so wave vector dependence that is related, space dependence where we have a wave vector k, and time dependence where we have a frequency omega. Everything is multiplied by this vector E. This is the vector that represents the direction of oscillation of the ion. So in this way, we are saying that this ion in position R is oscillating with this frequency and with this wavelength along the direction that is represented by E. Okay. In this configuration, we have a wave vector k. What may we say concerning wave vector k? If you remember, we had a similar problem with when we used the Sommerfeld approximation, and we had also a similar problem when we discussed the
block theorem and the results of the block theorem with the applying the block model to describe the electrons. In that case, we applied the Born von Karman boundary conditions. And thanks to the application of those conditions, we had the opportunity to find propagative solutions of the Schrödinger equation. In this case, we again look for a wave that describes a propagation. So we are looking for a wave that propagates through the solid. And as we don't want to consider surface effects, so possible reflection of this wave against the surface, we just apply exactly the same boundary conditions. In this case, the boundary conditions give us the same solution, the same result that was found for Bloch electrons, because in this case, we apply the boundary conditions knowing that we have an underlying lattice, and in this part, we are actually discussing the properties, the behavior of the lattice. So the boundary conditions are exactly the ones we have applied for the Bloch model. So what the final point is that the K vectors are the K vectors that are described with using, let's say, if we use the cubic lattice approximation, we have 2 pi over ax times an integer divided by the number of ions along the x direction. Then we have 2 pi divided by ay, another integer divided by ny, the number of ions in the y direction. And then we have 2 pi divided by az, and z, an integer divided by the number of ions that we have in the z direction. So this is just fine for cubic lattice. So the general expression for the wave vector k is exactly the same expression that we had for the Bloch electrons. So for the moment, we know that the wave vector k is defined in the reciprocal space, and the wave vector k may be a vector belonging to the reciprocal lattice, but in general, wave vector k is not a vector that corresponds to a vector of the reciprocal lattice. So as we saw for Bloch electrons, the reciprocal lattice is just a subset of the possible vector values that we may express using this specific expression for k. So yeah. Yeah. It just is, let's say, it's just because in place of writing sum over r prime alpha beta u alpha r d alpha beta u beta r prime. So with expressing all the indexes, we just write that in a more compact way. So this u is, actually a vector now. Also A is a vector. So this is the so-called polarization vector that tells you what is the direction along which you have the oscillation. And so U is actually, a vector now. So here also we have U of R vector and U of R vector. Now, at this point, I should apply this hypothesis into the Hamiltonian. But the calculation to, let's say, the end of the calculation, say the calculation does not last just a couple of minutes. So if you don't mind, I prefer to anticipate the break slightly. So we make the break now, and after break, I make the full calculation of that. And then, so I have the opportunity to also discuss the result of the calculation. And because again, the calculation is not short. So I just ask to those who are connected if they have comments or questions concerning what we have seen up to now.
No question.
Okay, so now I stop the registration.